Hello students. In this lesson, we are going to go through chemical bonding worksheet 2, and in this worksheet, our focus will be covalent bonding. Okay? Alright, before we jump into going through of the answers, let's do a little overview first, alright, to kickstart this transition to the next part, which is covalent bonding. So if we look at chemical bonding as a whole, we have learned that there are two types of bonding that we have learned for combined science chemistry: ionic bonding and covalent bonding, right? So the big idea, the big picture will be that ionic bonding would involve metals and non-metals. So for instance, in the case of, say, sodium chloride, which is an ionic compound, it is made out of the metal sodium together with chlorine, which is the non-metal, right? So in ionic bonding, essentially the atoms, they will gain or lose electrons in order to attain the stable duplet or octet electronic configuration. So it is about the oppositely charged ions, right? The cations as well as the anions attracting together with this strong electrostatic forces of attraction, thereby forming our ionic compounds. And then in terms of our dot and cross diagrams, this is how it looks like. Covalent bonding, on the other hand, if we just look at it side by side, right, let's compare and see what are the differences. So for covalent bonding, it's only involving non-metals, right? And in this case, our atoms, they will share electrons, but also in achieving this similar end goal of having the stable duplet or octet electronic configuration. All right. So in the case over here, we look at the element chlorine, which exists as a diatomic molecule. Di means two. So this molecule chlorine is made out of two atoms. Okay. So you can see very clearly in the dot and cross diagram, it's very different from that of ionic bonding. Okay. For covalent bonding, in your diagram, you need to show the electron shells overlapping, the valence shell overlapping, and then the shared electrons are found in the middle of this overlapping part. Okay, let's look at question 1. So we have a table with many examples. You are given the name of the substance. You are supposed to figure out the chemical formula as well as to draw the dot and cross diagram of the covalent molecules. Okay, so yep. So in the recap just now, we said that covalent bonding, we are focused on the sharing of electrons. Okay, so let's look at the first question. We have chlorine. All right, so chlorine, this one, from our prior knowledge, we already know that being a group 7 element, it exists as a diatomic molecule. Di meaning, you think of the word double, double means two, right? So chlorine uh, consists of two atoms, which makes up the molecule Cl2. So if we look at chlorine element, the electronic configuration is 2.8.7. And also at this point, you notice that whether you are doing ionic bonding questions or covalent bonding questions, the so-called working is and thought process is always similar. We should always first step look at electronic configuration. Okay, so if you look at chlorine 2.8.7, right? Um, it currently needs one more electron to achieve the stable octet electronic configuration. So the way to do covalent questions, the simple way, in my opinion, to share with you is like this. If let's say chlorine needs one more electron, then the thought process is that chlorine needs to share one electron. It needs to contribute one of its electron into the sharing to form the covalent bond. Okay, so if you look on the right hand side here in my dot and cross diagram, you notice over here I drew out all the electrons in all electron shells. So 2.8.7. The chlorine on the left hand side, the electron is denoted by the dot. And you can see over here, this is where the valence shell comes into this overlap, right? And this one electron that each chlorine atom shares is right in the middle of this overlap here. Okay, so you can see one dot and one cross, each representing the electron of one of the chlorine each. Okay, and then after you draw your dot and cross diagram, always just do a quick check that around each chlorine atom you have the stable octet, which in this case you do, right? 1, 2, 3, 4, 5, 6, 7, 8 electrons, and similarly for the next chlorine atom as well. Yes, I wanted to show you the structure of chlorine molecule. Um, if you can just look at my webcam, okay. Yeah, so this would be the structure of Cl2 chlorine molecule. You notice here there is this gray color part. This is the single covalent bond that is formed from the sharing of one pair of electrons between these two chlorine atoms. Okay. Okay, then now let's look at question 2 for oxygen. So same thought process, all right? So oxygen is also one of our diatomic molecules. So the chemical formula for oxygen, therefore, is O2. This one we are very familiar by now. So now let's work through the steps. So oxygen atom on its own, electronic configuration is 2.6. So following the same method that we went through with chlorine, notice here for oxygen now it needs two more electrons to be stable. So in this case for covalent bonding, an oxygen atom would share two of its electrons. So now if we look at the diagram here, it is shown in correspondingly as well. So you notice for our oxygen is on the left hand side, I've used the cross symbol to represent its electrons, and there are two that are being shared. Likewise, then another two is also being shared, as represented by the dot, and that is contributed by the other oxygen atom. Okay, so in this case, notice I also showed all the electron shells in my diagram, and at the end of my drawing, I will also want to do a quick check that around each oxygen atom, the valence shell contains a stable octet, right? 8 electrons. If you just count together with me, see 1, 2, 3, 4, 5, 6, 7, 8. Then the same for the other one. So this is our O2 molecule. And in this case, because there's a sharing of two pairs of electrons, so in terms of the molecule itself, if you look at my camera there, you will see that it is a double bond here. Okay, yeah. Let's now look at question 3. So in the earlier two examples, we saw molecules of elements. So now from question 3 onwards, we'll look at molecules of compounds. Okay. So water, everybody knows that it's H2O, the chemical formula. So if we break it down and look at each element on its own, we have hydrogen as well as oxygen, right? So hydrogen has an electronic configuration of 1. So it would strive to be like helium, all right? So trying to get stable duplet, and in this case, it will require 1 electron to form stable duplet, right? And oxygen, on the other hand, is 2.6, so it would require 2 more electrons to form stable octet. So following this train of thought, we know that each oxygen atom will have to share 2 electrons, of which it will be each received by a hydrogen each. So that's why we know that water should have such a shape. Okay, and in fact, we also know that water looks like this. I've also shown this to you in class many times, right? This is our so-called Mickey Mouse shape. Okay, or maybe I should hold it like that. Okay, the Mickey Mouse shape. Yeah. So if you look closely at the dot and cross diagram, maybe now I should hold the molecule like this, right? You can see that if you draw your dot and cross diagram correctly and properly, you will actually get the exact same shape of the molecule that I'm holding in my hand. Okay, so again, let's quickly run through. So each hydrogen will contribute one electron into the covalent bond. The other one comes from oxygen, right? So over here, you can see that overlap here. And then likewise on this side that I'm showing using the cursor. And then again, before you move on with life, check that around each hydrogen, indeed, there's two electrons, stable duplet. Likewise for the other one. And then around your oxygen atom here, it is also stable octet, right? 1, 2, 3, 4, 5, 6, 7, 8. So this is your correct diagram for water. Okay, question for ammonia. Ammonia is NH3, so it consists of nitrogen and hydrogen, right? So hydrogen, okay, we saw this previously already. So hydrogen needs one more electron to form stable duplet. Nitrogen is 2.5 for its electronic configuration. So in this case, it's 3 electrons away to attaining stable octet. So in this case, we know that each nitrogen atom will need to contribute 3 electrons in total to the other non-metal for sharing, right, in the covalent bond. So since just nice we have hydrogen, which each requires 1, so very nicely nitrogen will contribute 3 to another 3 hydrogen, so therefore NH3. Okay, over here the question only requires you to show outer shell electrons, so it's slightly easier in this case. And notice over here, this 3 pairs of electrons will result in the formation of that covalent bond. And then if you check against each hydrogen atom is a stable duplet, and then around the nitrogen atom it's also 1, 2, 3, 4, 5, 6, 7, 8 electrons, which is the stable octet electronic configuration. So at this point, I just want to remind you also that it is a very good habit to include a legend so that in a way to really remind yourself that you need to use the different symbols, the dot and the cross. Okay. Okay, let's look at question 5, methane. So methane is CH4. Hydrogen again is the same as what we saw. Carbon is 2.4. So in this case, it needs 4 more electrons to form stable octet. Therefore, carbon in methane will share a total of 4 of its electrons. So yep, each of them shared with another one from hydrogen. So if we draw all the electron shells, then this is how the dot and cross diagram will look like. Again, check that your shared electrons are drawn in the middle because it belongs, now that it's, share, so it belongs to both carbon as well as hydrogen. Okay, and then again, good habit, have the legend over there. So stable octet around your carbon, stable duplet around all your hydrogens here. Okay, finally, let's look at carbon dioxide. So carbon dioxide, we also are very familiar that it's CO2. And even if you happen to forget that it's CO2, you can figure it out yourself because carbon dioxide, right? So D, so think of the word double. Double means 2. So carbon dioxide means CO2. And then so carbon is 2.4. Just now we saw that it therefore needs to share 4 electrons in order to achieve stable octet. Then oxygen is 2.6. It will need to share 2 electrons. So over here, carbon dioxide is a little interesting. You notice each carbon atom will need to share 4 electrons, but we only have 2 oxygens here, right? So then the question is, how are we going to draw the dot and cross diagram then, right? How are the electrons going to be shared? So one way to see it is you can just do some simple math, right? You take 4 electrons divided by these 2 electrons, then you realize that you actually have to share 2 pairs of electrons. So this will give you a little clue that in carbon dioxide, what you should be drawing will be double bonds, as you can see in this another form of representation here. And in fact, at this point in time, I will also hold up a carbon dioxide molecule. Okay, And you can also see side by side at my webcam together with the dot and cross diagram in my answer. You can see that the diagram really reflects what the actual molecule looks like. Okay, so you have a double bond between carbon and oxygen on both sides. And then if you look at the entire molecule holistically, you also notice that it is a linear molecule. Linear meaning it's very, it lies on the same plane, it is straight. Okay, so yeah, if you follow my cursor, you see that there's two pairs of electrons shared here, likewise on this side. And if you do a quick count of the valence electrons around each atom, you notice over here around the oxygen, there's 1, 2, 3, 4, 5, 6, 7, 8, stable octet. Same for the other oxygen. And then finally, even for the carbon that's in the middle, it's also 8. 1, 2, 3, 4 on this side, 5, 6, 7, 8 on the other side. Okay, so this is carbon dioxide.